Good morning, everybody. Can you all hear me? It is my great privilege and honor to introduce our lecturer this morning, Rob Lowe, who comes all the way from London. But Rob is a Cape Townian by birth and education. It is here where he finished his schooling at the Jan van Riebeeck High and studied at the University of Cape Town, where he graduated with a master's degree in chemical engineering. It is also here where his early working career began, and it started at Science Fibers in Cape Town, which was followed by a 3-year stint in London as technical liaison manager. He returned to South Africa as managing director of South African Trioxide in Amanzimtoti before he was permanently transferred to the UK in a senior management capacity at the Trioxide Group. This company was subsequently bought over by the Huntsman family, and Rob became their commercial director with responsibility for the company's global commercial activities. He retired in 2005, but his life in retirement seems to be far more interesting. In retirement, Rob has followed a number of pursuits. He's a qualified coastal skipper, he's a very keen photography, and he's an associate member of the Royal Photographic Society. He teaches photography to members of his local camera club. He also lectures physics, in particular special relativity and wildlife, to various U3A group and A-level students in the communities near him. He also does his best to keep up with modern scientific developments, especially in the fields of relativity, astronomy, astrophysics, particle physics, and quantum mechanics. Wow. He lives in the village of Stokesley, is that correct? Yes. Stokesley, near the North York Moors in northeast England. Let us welcome him. Thank you.
Well, thank you. Thank you for the introduction. Yeah, I'll get it. Okay. Welcome, everybody. Just doing a quick scan. I think the average age here is one of the lowest I've ever seen in one of these lectures at the UCT Summer School. Great to see so many learners, scholars here today. It's fabulous. I hope I will stimulate an interest in the subject of physics, because maybe when you progress next year to university level, you could follow a career either in physics, engineering, or related fields. You should all have printouts of the lecture slides. They don't agree quite with what I've got because they've been modified and corrected since I issued them. There are 1 or 2 typos in there. Like light is not an acceleration, and neither does it only move at 3 meters a second. The objective of the lectures is really to take you through from the beginning, the basics that you need to know to understand relativity, right through to E equals mc squared, Einstein's famous mass-energy equation. That'll take a little bit of time to get there, but today I'm going to focus on reference frames. We'll then have a look at Einstein's postulates, his postulate about the laws of physics and the speed of light. And we'll cover the subject of simultaneity. These things form the absolute basis for understanding special relativity. Today is a non-mathematical session. Tomorrow there'll be a few more equations, and on Wednesday a few more. However, I have provided you with graphs that you can read, so you don't have to really understand the maths in any detail. I've just given it to you so that you can see where the graphs come from, and that hopefully you have a better understanding of what we're talking about, that I'm not just giving you a story, but that there is some substance behind it. If you have any questions, please ask, but if there's no time during the lectures and you think about it afterwards, you can just email me. I have got my laptop here, it's working, and I can respond to emails if you can send them through to me. So there's my email address there. Okay, we've got quite a lot to get through, so I'm going to get started right away, and we're going to start off with reference frames. What's going on here? Okay. I think what we all understand, or hopefully understand, of a reference frame is something that looks like this. This is a three-dimensional Cartesian reference frame. You've got the x-axis, the y-axis, and the z-axis. This is fundamental to explaining anything in physics. Something happens in a reference frame. For the purposes of special relativity, we're going to assume that all of these axes stretch infinitely far in all directions, backwards, forwards, inwards, outwards, everything. And somewhere in that frame, we may be located. There can be a second frame, but I've called this the X, Y, and Z prime frame. Now, you might be present in this frame. If you were in an aircraft traveling at fixed speed, and this was a train on the ground, there would be two different reference frames. And if we conducted any physical experiments in either of these two, you would get the same result. Not when they're accelerating, but when things are traveling at a constant speed. Let's just move on. Yeah, we have it. Oh, what I should have mentioned, let me turn that one that way. Of course, each reference frame has an origin. And this is the point which we would call zero. We can imagine this reference frame consisting of an infinite number of meter sticks, and in all directions. So you could have this lot going up here, you could have others going out there, another one there. So in other words, I can define the position of anything within this reference frame. This whole frame is full of invisible, or rather non-dimensional meter sticks, because you can walk through. They're transparent. You can walk right through them. They're not physically there, but you can measure distances. I could measure distances to anybody here in the audience using these, and from that I can locate the position of something happening. Okay. I think I might just need to work over here. Okay, as I've said, we've got the X, Y, and Z coordinates and the origin, which stretch infinitely far in the three directions. And we fill the space with a set of a lattice of meter sticks. Those sticks are not actually a meter. It's an Americanism, I'm afraid, but by that I mean something that has a fixed length. Now, in the reference frame, we'll have a whole lot of experimenters that will be equipped with clocks, like these. So at every intersection of meter sticks, wherever we get an intersection, say like that and like that, we would put an observer or somebody that can take a measurement. And something to remember when we're talking about special relativity, we take the measurements at the point where the event takes place. So you would need an infinite number of sticks, and you would need an infinite number of clocks and an infinite number of observers to do everything. But usually we can place them more or less where we expect the event to happen, so we can get it there. We don't rely on a light signal traveling, all the way from the sun back to us to determine whether things are simultaneous or not. We would have somebody at the sun with a clock which is telling the same time as the one on Earth when we take that measurement. That's how we would set things up. An important point is that the experimenters themselves are at rest in the reference frame. They don't move. If there's somebody sitting in this reference frame, if you're sitting on an aircraft, or you're sitting in a train, or you're driving in a car, you're sitting in a stationary position within your frame. So to you, nothing is, you're not moving, it's the other guy that's moving, and of course the other guy thinks it's you that's moving. Okay, so for accuracy, we'll put in as many measurement points as we can. And as I mentioned, this allows us to specify where an event happens. But in order to fully define it, we need to give something where what the time is as well. So you'll have the three space dimensions. We'll go back here again. You could have three space dimensions, rulers everywhere, and clocks at those interfaces, and there'll be another one up here. So we immediately notice that we're not working in 3 dimensions anymore, but we're working in 4 dimensions. Okay? Because you can't visualize a time dimension other than these 3 dimensions that you've seen here. You can visualize the spatial coordinates, but when you put time on top of it, it's difficult to form a picture of what a 4-dimensional entity would look like. And it's a fact that our neural architecture is wired up for 3-dimensional observations. As a human, we can't imagine 1, 2, or 4 dimensions. You can only imagine 3. Some people think they can see 2, but it's a subset of 3, and 1 dimension is a subset of 1. Of 2, sorry. We just aren't wired to do it. So effectively, you need to train yourself, and this is what physicists have got to do, because it leads to counterintuitive conclusions, trying to think about multidimensional space. And in pure physics, they go up to many more dimensions than 4. So a reference frame is a coordinate system for both space and time. Consists of the x, y, z, and t axes. So it's got a 4th axis that you need to remember. And these are the 4 space-time coordinates. As I've said, we can imagine that there's a clock at every point where the meter sticks intersect. And what we will do is we'll set them so that they're synchronized and read 0 when t is 0. If I were comparing 2 reference frames, I could put them together to start with. We could set the axes to, this point would be 0, 0, 0, and that one as well. And we could set the clocks to the same time. However, the moment those 2 axes start moving relative to each other, the times on the clocks are going to start changing. We'll come back into a little bit more detail to explain what that's all about and what it means. This is just a pictorial representation. Let me just get this thing working. Where is it? It's not shining. Wait a minute, it's this one, sorry. Yeah, you've got well, you're just showing 2 axes here, x and y. This is the reference frame, which I've called S, sorry. And in it, you've got these meter sticks, and at each intersection, you've got a clock. And these clocks, if you look at them, they're all telling exactly the same time. Of course, it's 3-dimensional, so it comes out in this plane as well. It's a cubic structure rather than just a 2-dimensional structure, as I've shown there. So and if an event occurs, say at this point over here, you would measure the time on the clock nearest to it, and you'd take the coordinates from the meter stick nearest to it, and that would define the event. Yeah, it can either be regarded as a real or more realistic, an imaginary lattice of meter sticks together with a synchronized set of clocks at every point. Now, for the purposes of this presentation and in special relativity, we only really need to consider 2 frames that are moving relative to one another. Obviously, there could be many more, but the mathematics in that would become extremely complex. So we'll just keep it to 2. And here's the setup that we would have with 2. You've got the S frame with its x, y, and z coordinates, and you've got the S prime frame, which is x prime, y prime, and z prime. And these 2 origins coincide at time equal to 0. The S prime frame, The S prime frame is moving to the right at velocity u, but it could equally move to the left, and you just have to reverse the signs. The axes are aligned, so they've got the same orientation. And the beauty about doing any special relativity work is if you've got something moving in a straight line, you can always align the x-axis with that moving object, and that then forms the basis for what you would call the straight line movement in the x direction. And this is u is the relative velocity, so s might be standing still, and s prime could be moving at about half the speed of light relative to that. And if you're in the S prime frame, you will see things differently to what somebody in the S frame will see. Maybe you could just imagine, the two. This one could be, this is a train. This one could be moving along here. This frame could be there, Mother Earth. Once the train's got up to a fixed speed, you can imagine the reference frame moving with it. Einstein used the concept of thought experiments to illustrate things and work out some of his phenomena, and he always used a train, trains that travel at very high speed. So beside the coordinate axis and the origin, a reference frame may be associated with an observer who, with the help of assistants, can use all the meter sticks and clocks to make accurate time and position measurements. And the length of the meter sticks can be adjusted to give us the accuracy we want. If I assume that you are sitting still in the center of the front row of the lecture theater, we have somebody there, and we've filled this lecture hall with meter sticks and clocks at rest in your frame. Let's call it the S frame. I'm also in the lecture hall, but instead of standing still, I'm going to walk around. And I'm going to walk around carrying a set of meter sticks as well. Maybe I'll just carry the frame with me. It'll be a bit easier. And we'll call this as the S frame. And obviously, my coordinates are different to yours. You'll express the coordinates as x, y, and z. I'll say they're x prime, y prime, and t prime. And we have a familiar event taking place every day. The noon gun at Signal Hill fires at 12 noon at the same location every day. So it's an absolutely fixed reference point. Thank goodness it is, and it fires very accurately. So we know exactly what the location of that event is every day. And it could just as well be in the S reference frame, the one I'm using over there, because it's not moving relative to us. If I'm moving relative to you with these frames, we'll agree that there's an X, Y, and Z frame, but you will notice, I will say my nose is 2 centimeters or 3 centimeters in front of my face to face. But you'll say, no, my nose is moving. Agreed? So already you can see that from the point of view, while I'm in this reference frame, I'm to all intents and purposes standing still. I'm not moving because the frame's moving with me. I'm not moving in this frame. But you see something different. Okay. Okay, I've mentioned that. The other one is if I walk past here and I scratch my nose after 2 seconds, I know that that time is 2 seconds. Now you're going to tell me that you're also going to measure 2 seconds, and unfortunately at the speed that I'm walking, you will. But if I was in a rocket ship traveling at 90% of the speed of light, you would measure a completely different time from the time I start walking to the time I scratch my nose. Will be different when you look at it from the point of view of a fast-flying rocket ship. It will not happen at the same time as I say, 2 seconds. It will be a completely different number. Okay, and this is where relativistic physics starts to depart quite a bit from Newtonian physics. And the problem is that only clocks belonging to the same reference frame can be synchronized. So these 3 clocks that I have here, I could put them into this reference frame, and I could set them up so that they've all got the same time. And that reference frame can move as it likes. All of those clocks will remain synchronized. However, if I had a different set of clocks in this frame, the time that is on these clocks will start to differ from the time on those clocks as soon as that frame starts moving. And this is perhaps the first notion of space and time are getting actually swapped out, interchanged, and it's real. This is not imaginary. You can measure it with the right equipment. It happens for real. So it's wrong to assume that clocks in different reference frames can be synchronized. What you would have to do, incidentally, if you wanted to synchronize a clock in a reference frame, the only way you could possibly do it would be to measure the distance. Let's supposing you had a light source here at the origin, and you had this thing 1 light year away, and this one 2 light years away, and this one half a light year away. You would have to set the time differently on these clocks, and then send the pulse out. And as it passes each clock, you start it going, so that you know that the clock is reading, that, like if this one was a light year away, well, let's make it something simpler, a light second away. You would have to set it 1 second, you'd have to rewind the clock by 1 second. As soon as the light pulse comes to you, you start the clock. Now it's running, this clock and the light pulse here was sent at the same time. And so you would do more and more of it as you send the thing further away. Okay. The problem with this is, because the speed of light is constant, you cannot get times between reference frames to synchronize. We'll cover this in some detail later on. So that's just a basic introduction to Cartesian reference frames. Now we're going to look at a special set of Cartesian reference frames, and that is what we could call let me come back to that, an inertial reference frame. Obviously, there's more than one set of reference frames that you can use. I've only used 2 here, but you could use spherical coordinates. You could use a whole lot of different frames, all pointing in different directions, but we don't need to for the purposes of our exercise. We only need 2 reference frames to properly define relativistic events. And these need to be inertial reference frames. And what we mean by an inertial reference frame is one in which an object with no external forces acting on it moves in a straight line with constant velocity. And that's why Einstein often used the trains in his thought experiments. That would be a straight piece of track there, and he would send a train down nearly at the speed of light. As long as your speed is constant, then the laws of physics are going to be obeyed. As soon as you start changing it, you start accelerating it, things start to fall down. So not all frames are inertial. But let's suppose in your frame is inertial, and we'll call it S, and I suppose I throw a ball at you through the hall. If I happen to be pacing backwards and forwards, while I'm pacing in one direction, that ball will be traveling in a fixed direction, and you will see it traveling but in a slightly different direction to the one that I see. However, the moment I turn around, if I'm walking up and down here, and I turn around. In order to turn around, I've got to accelerate because I've got to stop and come back again. I will then see all sorts of funny things happening. And the frame, as seen from my perspective, the ball will no longer be traveling in a uniform straight line. It'll be a curved trajectory. Okay. Okay, so in general, two frames that are both inertial must move with uniform relative motion along a straight line. Another shorthand way of saying it is that the S prime frame, say that frame, moves relative to this one at a constant velocity. And if you remember, velocity is a vector. So if your velocity is constant, you can't change direction. You have to keep going in the same direction all the time. And it's a feature of Newtonian mechanics that the laws of physics, F equals ma, together with Newton's law of gravitational attraction, are the same in every inertial reference frame. Think of it this way. Supposing I am an accomplished juggler and I'm standing waiting for a train to come along, and I'm juggling on the platform. The balls go up and the balls come down, and no problem. I can juggle perfectly. I hop onto the train, and as the train pulls out of the station, the juggling just goes to pieces. The balls fall everywhere. It's actually impossible to juggle while the train is accelerating. However, once that train gets back up to full speed, we're now back into a reference frame that is at constant speed. The juggling becomes an easy exercise as if you were on the platform. It could be like that in an aircraft. While you're taking off, you couldn't throw things up and catch them because the object would move. As soon as it's at cruising altitude, you can throw things up and down, and it's like being on the ground. It won't fall back where it started. Here we go. And the laws just simply don't work. Okay, when the train finally gets up to a constant velocity, the rules start to work again. Yes, if you're inside a sealed inertial reference frame, which is effectively where we are now, we can't feel ourselves moving, but we are moving around the sun. The sun is moving around the center of the galaxy, etc., etc. But none of that is obvious to us. Now, because the speeds at which we are moving are simply not high enough to detect that. If it were moving at an order of magnitude or a few more, then we would perhaps notice it, but we don't. And okay, maybe train travel is not so common in South Africa, but in the UK it is. And if you close the blinds in that, you cannot. It's very difficult on a smooth track to tell whether you're moving. Well, probably an easier one is when you're in an aircraft, when you're not going through turbulent air. You cannot tell that you're moving at 1,000 kilometers an hour, or somewhere of that in order that sort of speed. Okay, that's the juggling one. All right, any questions up to that point? All right, I'll move on to what special relativity is. Special relativity really is the science of the very fast. Things happen at and about the speed of light. That's where the world around you starts to change. It is quite different to Newtonian mechanics. Newtonian mechanics, incidentally, isn't flawed, it's just incomplete. Up to about, 20% of the speed of light, you pretty much can use Newton's laws of physics. Once you get beyond that, then you need to start making corrections. So the Newtonian view of space and time is that space and time are absolute. But this differs significantly from Einstein's correct view that space and time are relative. I mentioned it a bit earlier with the 4 dimensions. You've got to start thinking, and we'll hopefully get used to this, but that space and time are interchangeable. The time can become length, and length can become time. And these phenomena are actually real. This concept was introduced by Einstein in 1905. He was rather a young, dapper-looking man at that time. He had lots of girlfriends, and he had lots of intellect as well. But his concept was based on two postulates. And the first states that the laws of physics are the same in all inertial frames of reference, i.e. they are invariant. It's a big word, invariant, but that's what it means, that the laws are the same. The second states that the speed of light in a vacuum is constant. I'll come back to that in a little bit more detail. We actually mean the cosmic speed limit. It so happens that light does travel at the cosmic speed limit. They have profound implications. What's simultaneous for one observer might not be simultaneous for another observer. And later in this lecture, I'll do a thought experiment where we'll show what happens. When observers are moving relative to each other, they measure time or length, but they get different results. And that's what I've been trying to emphasize with when you start moving in different frames, what you see happening in the other frame is different to what the person in that frame observes. And thirdly, for the conservation of momentum and energy to be valid in all inertial systems, Newton's law and the equations for momentum and kinetic energy need to be revised. We'll do that on day 3. It's a little bit more mathematical, but obviously everything has to be revised, because if you're going to see if you're going to see the speeds of things changing relative to you, the question is what happens to the kinetic energy or the momentum? Well, it's not lost, it is still conserved, but there is some maths involved in computing it. Okay, so let's have a look at Einstein's first postulate, the invariance of physical laws. We have an example of the laws of motion being the same in all inertial reference frames, the juggler. What the juggler experiment said is, in one frame it worked, and once you got the train up to speed, the juggling worked, but in the in-between bit while you were accelerating, it didn't work. But once you got the two both moving, or one stationary, by stationary you mean relative to the railway track that the train is traveling on, then you can juggle. Another example is Einstein's of his postulate is the EMF induced in a coil of wire by a nearby permanent magnet. This was first discovered by Faraday in 1831. Some of those early physicists were brilliant because they had none of the background material that we have today, and it was Faraday that could relate magnetism to electricity, and it led to obviously the explosion of all the electrical devices we have today. Let's just take a quicker look at the phenomenon. We'll use the induction coil experiment now. Some of you have seen this. I'll rerun this experiment at the end of the lecture. I think I'm not going to start it up now. I'll just give you an explanation of what was going on here, but afterwards come back and come and have a look at this equipment working. But the objective is to illustrate that the EMF induced in an induction coil, regardless of the direction of movement of either the magnet or the coil, gives you the same result. And this is the simple explanation here. Sorry. Here you've got two magnets with north and south pole up there. You've got two coils, two identical coils. You've got two galvanometers, and they're going to measure the output voltage from these coils. On the left-hand side, you can see that the magnet moves at a velocity v into the coil. On the right-hand side, the coil moves at the velocity v over the magnet. And when you take the readings on these two instruments, you get exactly the same results. Now it looks trivial and it sounds obvious, but what that does do is we've actually got two reference frames, because in the one case the coil's moving, in the other one the magnet is moving, and provided the coils and magnets are identical, you get the same result. What that tells you, though, is that if one of these coils and magnets were perhaps on a train and another one, you were on an aircraft at constant speed, and you did the same experiment, you'd get the same results. I've got movies of that operating, and I've also got the equipment, but I'd rather go through the lecture points first and then come back at the end if there's time to have a look at that actually working. Well, I will show it at the end, so those who didn't see it at the beginning, please come and have a look at the end, and you'll be able to see it close up in operation. I'm going to skip these few. Okay, I'll come back to that later on. Einstein's second postulate, and that is that the speed of light in a vacuum is the same in all inertial reference frames and is independent of the motion of the source. In the early 19th century, scientists believed that there was such a thing as the ether, and that's what led to the transmission of light through space. The scientists then were thinking of something similar to the movement of sound through air, and they had to have the ether to explain how light traveled. But if this was the case, then the speed of light wouldn't be a constant, and it would be dependent on the motion relative to the ether, and this is not the case. In 1863, the brilliant physicist Maxwell discovered that light and all other electromagnetic waves travel in a vacuum with a constant speed. Maxwell almost got there. He didn't make the final leap that Einstein did, that by implications, if the light moves at a constant speed in an inertial reference frame, it must move at a constant speed between all inertial reference frames. He understood that it worked in one, but not, and he could understand that it would work in another one. He didn't realize that when you were observing one from the other, the speed was still the same, regardless of the movement of those two reference frames. But he did some other pretty clever stuff anyway. And then in 1887, there was the Michelson-Morley interferometer experiment, which put to bed the concept of the ether. From then onwards, people realized that light didn't need a medium to travel through. It could travel through a vacuum. Okay. History says Einstein was unaware of this experiment, because it would have made quite a big difference if these guys had got together with Maxwell, because they would have started to work out there's something going on here. But no, it was Einstein that did it. So in 1905, he said if Maxwell's equations are valid in all inertial reference frames, then the speed of light should be the same in all frames and in all directions. Einstein's second postulate thus states that the speed of light in a vacuum is the same in all inertial reference frames and is independent of the motion of the source. It doesn't matter which way the light is shining. If you shine a light while you're moving backwards, forwards, upwards, downwards, left, right, it leaves that position where the light beam originated. It travels at the speed of light, and it always travels at the speed of light. It's one value. Which is absolutely central to special relativity. If that were not the case, the special relativistic effects that I'm going to describe to you would not, in actual fact, take place. Now, the speed of light is pretty fast. It's 3 times 10 to the 8 meters a second, which is from the Latin word celerius, which means speedy. And it circumnavigates the Earth 7.5 times per second. A light beam takes 8 minutes to get from the sun to us, and I think it's 2 seconds from the moon and about 28 minutes from Mars, something like that. But that's the speed at which it's traveling. All right, so let's have a look at an illustration of Einstein's second postulate. Firstly, and that is that Newtonian mechanics correctly predicts the velocity of relatively slow-moving objects. But Newtonian mechanics goes wrong when you start looking at high-velocity objects. And here's the first one. This is a very Here's an observer in frame S. Here's on Earth. There's a rocket ship in frame S prime. And this rocket ship is traveling at 1,000 meters a second. Not particularly fast. And you can see the US prime. This is as observed by this guy down here. Now, if that rocket ship fires a missile at 2,000 meters a second, it's easy to work out what this guy here would see it as. It will be 3,000 meters a second. There we go. You just add it up. 2 + 1 = 3. And that's the correct answer. Simple. Now, let's look at the next example. Instead of firing a missile, the rocket ship now that's traveling at 1,000 meters a second shines out a light beam. And that light beam is going to travel at the speed c. So if I'm a rocket ship here, whether I'm going there, that light beam that I'm shining, going behind me, wherever I shine it, it's still going at 1,000 meters a second, as seen by this guy on Earth here. But if we were to use Newtonian mechanics, we would say, well, it's got to be c plus 1,000 meters a second. But nothing can go faster than the speed of light, so the answer is c. Here we go. All right, so that's the correct answer. Now, that's a fairly simple example again, but I hope it gets the concept across. But the speed of light never, ever changes. Okay. Yeah, by implication, it means that an observer cannot travel faster than the speed of light either. The rocket couldn't fire up, and I'll illustrate this later in the week. You could have, say, one rocket going off at half the speed of light, then you send off another one at half and another one at half. By the time you've added it all up, you're going at 3 or 4 times the speed of light. It doesn't work. The fastest the rocket can go is the speed of light. Strictly speaking, c is the cosmic speed limit, which at the fundamental level is the speed for any causal influence. That's quite important. The reason nothing can go faster than the speed of light, if it could, you could actually go back in time and start affecting things in the past which would have an impact on the present. It is absolutely impossible to go faster than the speed of light, and it's impossible to do time travel as well. For any of those who think maybe there is, it's not possible. But it's that causal influence that is the cosmic speed limit. It doesn't have to be light, but light, because it's massless, travels at the cosmic speed limit rather than the other way around. Because there are examples where light travels through water and then you get funny behavior. But only massless particles can travel at this speed. And by the end of the lectures on Wednesday, we will have derived this fact from first principles. Photons are massless, and hence they travel at the speed limit c. The only other known object entity that can do it are the gluons, which are the force carriers of the strong force in the nucleus. They travel at the speed of light. And gravitons, which have not yet been detected, also travel at the speed of light. I think the base gravitons will be, I would predict, they will be detected within the next 10 years. The equipment's getting there. It's not quite there yet, but it's not far away from picking them up. And we'll find that it travels at the speed. What that means is that if the sun were to extinguish itself right now, immediately, it would take 8 minutes before the Earth's orbit to change, because the gravitons would still be moving towards the Earth, and only after 8 minutes will we have no sun left to go around. This is a little bit of maths. The first rocket ship implied that the velocity had to be equal to v plus u. And clearly, if u is at the speed of light, then v is greater than the speed of light, so that's not possible. And obviously, this is an inconsistency which we'll have to resolve. And the Galilean velocity transformation cannot be precisely correct. And some very fundamental modifications in our kinematic concepts are required. And the first is the seemingly obvious assumption that observers in frames S and S prime use the same time scale formally stated as t equals t prime. I've mentioned to you on a few occasions, when your frame moves relative to my frame, your clock will move at a different speed relative to my clock. So the time, t in one frame, is not equal to t prime in the other frame. There's a relationship which we'll derive tomorrow. The observers must have different time scales, and the velocities, consequently, one is delta x primed over delta t primed, another one is delta x primed over delta t. That's what the Galilean transformation was using, but you can see that those two equations are not the same. And the real problem lies in the difficulty in the concept of simultaneity. We mentioned earlier on that what might be simultaneous to one observer is not simultaneous to another observer. This little bit's going to, what I'm going to show you now, is just concentrate because it's quite subtle what actually happens. It sounds illogical, but it's real. And we'll use a thought experiment. Einstein was very good at using these, and he tended to use fast trains in his thought experiment, and I'm going to do the same. And we'll have a look at what happens. Events are what really happen, but how do we determine the space-time coordinates of an event? And this is a problem of measurement. Remember that the reference frame is a coordinate system in which observers and their assistants make time and position measurements, but we just need to, before I go into the actual simultaneity, I'll just show you how the measurements are made. Here we have a frame. You've got synchronized clocks in the S frame, and you've got synchronized clocks in the S prime frame. Here's the S prime, there's the S. An event happens over here. Measured in this frame, it's got those two times in that location. But in this frame, that same event is happening at a different time and at a different location. Same event. That event there and that event there is the same thing. And an event is something that happens at a fixed coordinate and at a fixed time, like the noon gun going off on Signal Hill. That is what an event is. It's not a rock concert that lasts a week or something like that. It's an instant in time. It has no, in fact, the time at which it happens is instantaneous. Okay, so all these clocks are synchronized, and the measurement scheme is as follows. The X, Y, and Z coordinates of the event are determined by the meter sticks, and the event takes place at the nearest one. And we display the time. Okay. Did that make sense? Okay. All right, let's look at the experiment. Firstly, we're going to I'll introduce to you the concept of a thought experiment, and secondly, we'll look at what happens to simultaneity. So imagine we have a train like this one I had here, moving along a track. I'll use that track a bit more tomorrow. Actually, in the UK, I have a powered one. Fortunately, I've got grandchildren, so this is their Lego. And I have trains running up and down and lights flashing, but that thing didn't fit in a suitcase. So I just brought the tracks along. I didn't get stopped by customs either. I don't know what they would have said if they'd opened my bag and found that. Anyway, so here we have it. This is the high-speed train. Imagine it's traveling at something like 99% the speed of light. And what happens here is there's a bolt of lightning that strikes the carriage at point A prime and point B prime and the ground at point A and B. And for the purposes of this exercise, those are all simultaneous events. Okay, they all happen at exactly the same instant. In the train, you've got Sarah sitting in a carriage in the middle, and she's at O prime in the S prime frame. But that's her origin. And Peter's standing on the platform, and he's in the S frame. So he's stationary. This train is whizzing past at a super high speed. I've mentioned Peter's. What happens is that after the train is struck at A prime and B prime, a light front starts to travel. The one at the back of the train starts to travel towards the front of the train, and the one at the front of the train travels towards the back. They're both moving towards Sarah. Now, Peter's on the station. He's halfway between these two, but his wave fronts are also moving towards him. Think of the wave front as a light that was just, let me go back. No, I'm going the wrong way. Okay, here we go. As a light being switched on at the time that gets struck, and now the light beam is moving towards the people. You can see what's happening here. They're moving, the beams are moving at the same speed in both directions, but you can see that this beam here is going to be reaching Sarah before that one does, whereas with Peter, the two are going to reach him simultaneously. Yeah, away from me. Okay, so they're moving towards the people. Now Sarah is moving towards that side. The frame's coming. So you've got Sarah moving this way and the light moving that way. Peter's stationary. I think it's pretty obvious if you're moving towards the source of light, you're going to get there before Peter sees it. Let's see what happens. There you go. By the time the light beam has reached Sarah, the light front has reached Sarah, it hasn't reached Peter, and neither has this one from A here. Peter has seen nothing. So Sarah has seen a flash of light. Peter has seen nothing, but the train moves on. Okay. What eventually happens is that the two wavefronts meet halfway between A and B, which would also be where A prime and B prime were at the start of this exercise. And at that time, Peter sees two flashlights simultaneously. He doesn't see the one first and the other one second. But Sarah at this stage she's seen the front beam, but she hasn't seen the back one yet. It's only after they've reached Peter that we get there. And finally, the light beam reaches Sarah after the beam has passed Peter and the other one has passed Sarah. You can see what's happened. Peter says immediately, but these things happen simultaneously, and Sarah says, no, you're wrong. It struck the front of the coach first and then the back of the coach, because I know the speed of light is constant and I know the distances are the same. And if the speed of light is constant and the distance is the same, the time should be the same, but they're not. Silence. This is fairly fundamental to, it's not mathematical, this is just conceptual. Okay. Well, Sarah reasons that each bolt took the same amount of time to reach her because they both traveled the same distance at the same speed. And thus Sarah concludes that the first lightning bolt struck B before the second one struck A, and using similar logic, Peter says that they're the same. And in conclusion, whether two events occur at different x-axis locations are simultaneous depends on the relative state of motion of the observers, and that's one of the big lessons of special relativity. Light is constant, and things that take place simultaneously in one frame do not take place simultaneously in another frame. Okay? There's no basis for saying which one of them is correct, by the way. They're both correct. This is where special relativity does start to scramble the mind a little bit, but they're both correct. No